To American pilots, the J-20 is not a stealth fighter. It is a flying lighthouse. Beneath its cutting-edge frame, decades-old engines betray China's most advanced jet, igniting an infrared beacon visible far beyond radar range. While Beijing claims hidden power, the truth is brutal. Hardware built for secrecy is lighting up every missile and satellite in the sky. How did a program meant to rival the F-22 become so exposed? When the J-20 first rolled out, its promise of stealth and power rested on engines that belonged to another era. Early prototypes and initial production models relied on the Russian Saturn AL-31FN, a direct descendant of the late Soviet AL-31F designed for the Su-27 flanker. The AL-31FN brought proven reliability, but it was fundamentally a 1980s engine, built for brute force rather than subtlety. Its architecture prioritized thrust over low observability, and it lacked features now standard in Western fifth-generation fighters. No thrust vectoring, no advanced digital controls, and no meaningful infrared suppression. As J-20 production ramped up, China began to install its own Shenyang WS-10C engines. On paper, the WS-10C offered a modest step forward: digital engine controls, improved materials, and a thrust class in the 13 to 14-ton range with afterburner. But the gap with Western benchmarks remained stark. The F-22 Pratt & Whitney F119, for example, delivers nearly 16 tons of thrust and incorporates single crystal turbine blades, advanced cooling, and two-dimensional thrust vectoring nozzles. That engine is an entire generation ahead in both performance and stealth integration. The J-20 airframe was designed with the hope of a breakthrough in indigenous engine technology. Instead, its reality is shaped by inherited limitations. The AL-31FN Soviet lineage and the WS-10C incremental advances have left the mighty Dragon with engines that struggle to match the demands of a true fifth-generation stealth fighter. Thrust-to-weight margins are tight, supercruise is limited, and the absence of thrust vectoring narrows the aircraft's maneuvering envelope. The result is a platform forced to compromise, waiting for an engine that can finally deliver on its original vision. Development of the WS-15 engine began in the mid-2000s, driven by China's ambition to power the J-20 with a truly indigenous, high-thrust turbofan. The program was presented as a leap forward, promising to deliver the thrust, reliability, and high-temperature durability needed for a world-class stealth fighter. For nearly 2 decades, engineers at AECC and Shenyang worked to close the gap with Western engine technology, setting targets intended to match or exceed the performance of the United States F119. Progress, however, proved slow and unpredictable. Bench tests and flight trials throughout the 2010s revealed persistent challenges. Chinese state media issued optimistic updates, but Western and Asian analysts reported repeated delays and a lack of J-20 aircraft powered by WS-15 engines in operational units. The core obstacles centered on metallurgy, achieving the high temperature tolerance required for sustained thrust and long engine life. Reports describe difficulties with single crystal turbine blade production, quality control, and thermal barrier coatings, all critical for handling the extreme heat and stress inside a modern fighter engine. Anecdotal accounts of major test failures circulated, including unverified reports of a catastrophic test stand accident around 2015. No primary source documentation has surfaced to confirm a specific explosion or casualties, but the risks of high-thrust engine development are well known. The absence of operational WS-15 engines in frontline J-20 squadrons by 2024 underscores the scale of the technical hurdles. Despite repeated public claims of breakthroughs, independent analysts continue to report that WS-15 remains in limited flight testing, with no evidence of widespread service entry. The timeline of missed milestones and ongoing material challenges highlights the urgency and frustration surrounding China's quest for a truly competitive fifth-generation power plant. Inside every modern fighter engine, the hottest and most fragile parts are the turbine blades. These blades must survive temperatures that push the limits of metal. In the United States, single crystal superalloys have unlocked turbine inlet temperatures exceeding 1,600 degrees Celsius, enabling the F-22 F-119 engine to run hotter, smaller, and more efficiently. China's engine makers, led by AECC and private firms like CAST, have spent decades building up single crystal casting lines and mastering rhenium-rich nickel alloys. Yet Chinese technical papers and industry statements admit that mass production yields remain low. The challenge is not just making a single perfect blade, but producing thousands that can withstand extreme thermal and mechanical stress, cycle after cycle. Even with advanced vacuum furnaces and directional solidification, the average Chinese single crystal blade is believed to tolerate lower peak temperatures than its Western counterpart, by some estimates 200 degrees Celsius less. This shortfall forces designers to run the WS-10C and WS-15 engines cooler, which means larger nozzles and more airflow to achieve the same thrust. The result is a bigger, hotter exhaust plume that directly impacts the aircraft's infrared signature, giving adversary sensors a clearer target. Infrared sensors don't need a radar lock to find the J-20. The aircraft's round, axisymmetric nozzles expose a wide swath of hot metal and exhaust directly to the sky. Unlike the F-22's flat, shielded nozzles, these circular exits give heat nowhere to hide. The result is a plume that stands out against the cold background, especially when afterburner is engaged. Open-source thermal imagery and defense analysis consistently show that this design choice leads to a pronounced rear aspect infrared signature, larger and brighter than that of Western fifth-generation fighters. Modern IRST systems, like those fielded on advanced Russian and European jets, are built to exploit this vulnerability. In clear atmospheric conditions, a hot rear aspect target can be detected at ranges approaching 100 kilometers or more. The J-20's engine and nozzle combination, lacking both advanced IR suppression and two-dimensional shaping, creates a detection window that extends far beyond radar line of sight. For any adversary equipped with a sensitive IRST, the J-20's exhaust plume acts like a beacon, advertising its position across vast distances. This is not just an engineering footnote, it is a tactical reality that shapes every mission profile the aircraft flies. The J-20's canard delta layout stands apart from the smooth, tailless profiles of Western stealth jets. These forward control surfaces, essential for maneuverability at high angles of attack, introduce a persistent radar challenge. Each canard adds its own set of edges and moving surfaces, increasing the number of potential radar reflection points. Electromagnetic modeling and open-source analysis indicate that canards, even when carefully aligned, can raise the aircraft's radar cross-section compared to a pure delta or tailless design. Some Western defense analysts estimate that the presence of canards can increase radar cross-section by a notable margin, though the exact amount varies by frequency and angle. The real vulnerability appears when the canards move. Every adjustment, whether for pitch, trim, or stability, creates a shifting geometry. This dynamic motion can produce brief but measurable radar spikes, as the surfaces rotate into positions that reflect radar energy directly back to a sensor. Flight control computers attempt to minimize unnecessary movement, but in practice, the constant fine-tuning required for stability means the J-20's radar signature is never entirely static. The result is a stealth profile that, while still advanced, offers more opportunities for detection than the more unified shapes of the F-22 or the F-35. For adversary radar operators, these fleeting spikes can be enough to cue tracking systems or trigger engagement windows, adding a radar vulnerability to the J-20's growing list of signature challenges. Mission planners working with the J-20 face a hard ceiling on both speed and range. Open-source flight data puts the aircraft's sustained top speed at Mach 1.2, well below its advertised maximum. When pushed harder, engines overheat and the airframe vibrates beyond safe limits. Fuel consumption becomes the next hurdle. Analysts estimate that the J-20 engines burn at least 20 to 30% more fuel than the F-22 in comparable regimes. On paper, official figures claim a combat radius of 1,100 kilometers, but operational profiles, including high-speed ingress, evasive maneuvers, and afterburner use, shrink that real-world reach to something closer to 700 kilometers. Every kilometer lost to fuel burn narrows engagement options and forces earlier returns to base or tanker. In a contested environment, that means less time on station and fewer chances to control the fight. Meanwhile, adversaries like the F-35 equipped with advanced sensors and longer-ranged missiles, can exploit these limits, shaping the geometry of every encounter before the J-20 is even in range. Assembly technicians at Chengdu face a reality few Western aerospace plants would tolerate. Each J-20 engine often requires hand-fitted assembly, with parts adjusted individually to achieve a workable match. This process means components from one engine may not fit another, complicating repairs and logistics. Internal reports, rarely confirmed, suggest high rejection rates on the assembly line. Some estimates put the figure at more than half of engines failing to meet final standards. The result is a limited pool of airworthy power plants and a bottleneck on production. Official claims of 300 operational J-20s are disputed by outside analysts, who count fewer than 200 in active service. Anonymous pilot accounts describe a preference for the older J-16, citing fewer in-flight shutdowns and less time spent managing engine quirks. Maintenance crews report frequent troubleshooting and inconsistent performance. For a fighter meant to project power, these manufacturing issues quietly erode fleet readiness and pilot confidence. Right now, technical limits, not just ambition, define the J-20's role in Asia's contested skies. As detection technology advances, stealth without true invisibility loses its edge. In modern air combat, what you cannot hide may matter more than what you claim. The real battle is for credibility.